Hey, welcome back. So I said at the very beginning of the course, we had a little math. The whole section's pretty mathy, but this last video in particular is condensed with some math. We're talking about logarithms, as you can see. Whether you learned about logarithms at one point, or you learned about logarithms at one point and forgot it all, or you never learned about it, I'm going to try and just make it pretty simple and also quick, because it doesn't actually matter that we're masters with logarithms. The reason I'm even showing it to you, I guess that's where I should start, is that some algorithms that we'll see have a big O that isn't simple. It isn't big O of 1 or of n squared. These are very common complexities, and we've seen them, and I think they're pretty easy to comprehend, hopefully. But there are some big O expressions that involve some more difficult math or less common expressions. And something that comes up more than I personally would like are logarithms. So that's why I'm showing it to you. We will have, and I'll show you in a bit, some algorithms in this course where their time complexity, instead of being O of n, might be O of log n. So let's start with what's log? What's a logarithm? So put simply, a logarithm is the inverse of exponentiation. So just like division and multiplication are a pair, logarithms and exponents, exponentiation, are a pair. So here's what you might see. You would read this as log base 2 of 8 equals 3. And what we're really asking or calculating here is 2 to what power equals 8? So if we take 2 and we raise it to some power, what power will give us 8? 2 times 2 times 2, it gives us 8, so the answer is 3. So 2 cubed equals 8. Here's just that same thing written down again. Log base 2 of a value equals the exponent. You can switch it around and say 2 to the exponent equals value. Just like if we had 1 divided by 2 equals 0.5, you could switch that around and say that 2 times 0.5 equals 1. We can move things around. They are the inverse, exponentiation and logarithms. Now, logarithms aren't always working with base 2. You could have log 3 of something. 3 to what power gives us 8, or log 5, or log 10. The most common ones, though, are the binary logarithm, which is log 2, so 2 to what power. Then there's also the base 10, so 10 to what power gives us some answer. Then there's also log e, which I'm not going to go into, but I probably shouldn't have said that anyway. There's a third very common algorithm. However, for what we're concerned about, we care about the big picture, and we're going to omit the 2. We're just going to say log, because first of all, it's annoying to write all this. Is this subscript? I think it's subscript, not superscript. It's annoying to format this, but also it doesn't really matter at the end of the day, because if we're comparing the graph of a constant time and a quadratic time and log n time, it doesn't really matter if it's log base 2, log base 3, log base 10. It's going to be the general trend that we care about. But just so that we're clear, this isn't actually a mathematical operation on its own. You can't just take the log of a number. You need to have a base. So we need to say log 2 or log 10. But in the slides and in literature, that sounds stupid, in literature, in things that you'll see online around big O notation, the shorthand is just log. If you want a rule of thumb, just to calculate it roughly, the binary logarithm of a number roughly measures the number of times you can divide that number by 2 before you get a value that's less than or equal to 1. So if we have 8, we're going to divide it by 2, and it's still greater than 1. So we're going to divide by 2 again. It's still greater than 1. Divide by 2 again. Now we hit 1. So that means 3. We divided 3 times, so the answer is 3. 25, however, it doesn't go cleanly. There's no way of dividing it by 2 evenly. So we divide by 2, and by 2 again, and again, and again, and then we're finally below 1. So this tells us that it's 1, 2, 3, 4, somewhere between 4 and 5. And the answer is 4.64. So the actual calculation is not that important. What matters here is if we take a look at it on a chart. So logarithmic time complexity is great. If you have an algorithm with log n time complexity, I'll show you which one it is here. Here we have constant time in red. And then right above that in orange, we have big O of log n. You can see that up front, it's a little steeper, but then it really tails off and is very gradual. And this is great. If you have an algorithm with log n time complexity, fantastic. So that's why I'm showing it to you, because it compares very favorably to things like O of n. There's another common one we'll see, n log n. I'm not going to go into examples just yet, but both of them involve logs, so I figured I should show you. It's not as good, but it's still better than something like n squared, the quadratic time complexity. So really the point at the end of this section, even if you're stuck on some of the math, what I hope we have is that later in the course, I'll show you two algorithms. I want to be able to point to one and say, this one has log n time complexity, this other one has O of n time complexity. And I hope that you can look at this chart and understand that, cool, the first one is better. It's at least more efficient, it's faster, because log n is much better than O of n. The larger n gets, it doesn't grow that much, the runtime, with log n, but it grows a lot in proportion with n for O of n. Okay, so that's why I'm introducing it here. We have a bigger picture of, these are the most common big O expressions. Like I said, the math, we don't have to worry about too much, but I just wanted you to know what a log is. Let's talk about where this will come up. So certain searching algorithms do have logarithmic time complexity, and we will see those as we go and progress through the course. Also, efficient sorting algorithms involve logs. So not all sorting algorithms, but some of the more efficient ones do. So we'll see that as well. And then finally, recursion, another topic. So basically there's three reasons here, none of which we've actually discussed. So this might not make a lot of sense. I'm basically saying in the future, we're going to see it at this place, and this place. Searching algorithms, efficient sorting, and recursion. And that has to do with space complexity with recursion, not time. So hopefully these will make more sense once we get there. Really, again, it comes down to just having this nice picture here. If I was teaching this in a classroom, I'd have this up on the wall at all times, like laminated, printed out, and I'd have a long stick, and I'd whack it on the wall and point it for every algorithm, point at one of those lines. And I'm going to try and kind of do the same virtual thing in this course online. Okay, so let's do a quick recap. We covered a lot. To analyze the performance of an algorithm, we use big O notation. It has to do with big, high-level, big picture trends. As the size of an input grows, we want to know how the runtime changes or how the space complexity changes. So big O can give us a high-level understanding of time or space complexity. It doesn't care about precision, just general trends. Time and space complexity as measured by big O depends only on the algorithm, not on the hardware. So yes, the actual time it might take to run one algorithm on my computer compared to some supercomputer will definitely be different. But the general trend won't be. Big O is basically measuring the number of operations that happen, whether an operation takes 10 milliseconds on my computer or 1 millisecond on another computer, which that's pretty slow anyway, but ignore that. And big O notation is everywhere, so we're going to get a lot of practice, and that's why it's coming first in this course. I feel kind of bad about it, like I've said before, because it's not the most welcoming topic, and it's kind of a rude awakening, but it gives us a context to discuss things. I'm going to go back to that terrible analogy of the Richter scale with earthquakes. It gives us a way of discussing how earthquakes compare their magnitudes. It's the same idea. We can compare algorithms now and say, oh, this one's great, this one's terrible, because its space complexity is X, or its time complexity is X. Anyway, let's call it a day here. Let's stop now. And we'll see you in the next section.